MLSS 2021. It is my great pleasure to introduce today's speaker, Professor Philipp Krähenbühl. Philipp is a professor in the Department of Computer Science at the University of Texas, Austin. He received his PhD in 2014 from the CS department at Stanford University, and then he spent 2 years as a postdoc at UC Berkeley. His research interests lie in computer vision, machine learning, and computer graphics. He's particularly interested in deep learning, image, video, and scene understanding. He has many influential work in computer vision. I believe many of you have heard his work about unsupervised visual feature learning, for example, bidirectional GAN, that is by GAN, and feature learning by impending. And today, Philipp will share with us how to use advanced deep learning technology in computer vision. Please join me to welcome Professor Philipp Krähenbühl. Philipp, now the stage is yours.
All right, thank you very much for this wonderful introduction. So today we're going to talk about computer vision, and this is going to be a very broad topic. And so we're going to cover a lot of different things, some of it pretty shallow, but if at any point you want to know more about what's going on, feel free to interrupt me with a question. You can just post it in the chat, and I'll make sure to just monitor the chat a little bit on the side here. All right. With that, let's get started. All right. The goal of computer vision really is to understand the world around us from images or videos like this one here. And so I'm not going to tell you where I took this video. I'm just going to play it for you real quick. And while we look at this video, I would like you to think kind of what might you want to know about what's in this video. All right. So the goal for our systems is really to understand everything. But what is everything that's in this video? I'm going to give you sort of a minute or two to catch up, and then let me know kind of what are the things that you would want to know that happen in this video. Don't be shy. Feel free to use the chat. I know it's early in the morning for some of you. So if there's no reply, I'll give you one. I'll start with one, and then I'll wait for the next one. All right. So one thing that you might want to know about this this video is what are sort of, oh, okay, we have one before I give one. Recognition, okay? So we have one reply that's recognition. So what is recognition? Recognition is kind of trying to figure out sort of what are objects or things inside of this this video. And yes, we just got another good reply that says object detection. Okay, where is the object? Yes, that would be localization. For example, here, if you would look at the bike. Now, there's more than just objects in this image. What else could you kind of tell about this image or the video? Another good answer is when was this captured, right? So what, like, for example, what season is it? What year? Also, what time, maybe time of the day. Then there's tracking, exactly. So not just what are the objects, but where do the objects kind of come from? Sort of where were they in previous frames? There is semantic segmentation, yeah, which is trying to figure out what is sort of the stuff in an image, anything that's not an object. There is how many people, which is a sort of counting. There is mapping, yeah, which is another task, which is trying to figure out sort of where are all the objects in relationship to one another on a metric map. Motion detection or motion estimation in general, yeah. So for example, if you look at individual pixels, where would these pixels have occurred in the previous frame? And there's many, many more. In fact, there's about 400 different computer vision tasks that are categorized and over 1,000 different data sets. And if you're interested in sort of what are all the different weird things people do in computer vision, I'd highly recommend you to look at Papers with Code. It doesn't just list computer vision, it also has natural language processing and related sort of fields in there. But it's a very nicely categorized source of sort of problems that people study. And so today, we're kind of trying to look at not these 400 problems, but sort of the overarching themes that cover most of these different computer vision tasks. And the nice thing about computer vision is that it can be categorized very easily into sort of a few different bins of what high-level tasks people look at. And the bins that we're going to look at today are going to be image-level tasks, which is giving you one answer for each image that you're looking at. That might be classification. It might be telling what time that picture was taken. It might be telling where the picture was taken. Then we're going to look at dense tasks, which are tasks that really sort of zoom in to every single pixel and try to kind of figure out what are the individual points or pixels in an image or regions in the image doing. And then we're going to look at sort of sparse tasks. And these tasks are by now make up the majority of computer vision. And they're somewhere in between trying to figure out just one label per image and trying to figure out what's going on at the pixel level. And then towards the end, we're going to cover some sort of temporal tasks. Now, I just bundled a bunch of them together at the end. They're not very nicely organized. But towards the end, as far as time allows, we'll just look at sort of how do people actually model videos or temporal signals in computer vision. Now, for each one of these topics, I'm going to spend about maybe 20-25 minutes giving you sort of a coverage of what's going on inside of that topic. And then we'll talk about 5 to 10 minutes about some exciting open problems that if you want to work in computer vision, you might want to look at. All right. And then after each of these topics, we'll have about a 10-minute break. And the time of the break can vary a little bit. So if you have a lot of questions, maybe the break is going to be a bit shorter. If you have no questions at all, the break is going to be quite long. And I'm going to be around during the break. So if you want to have any sort of discussion, any sort of questions answered that are sort of more open or don't directly relate to the lecture material, I'm more than happy to answer these questions in that break. All right, and if you have any questions about the setup, please feel free to post them in the chat, and I will just keep an eye on it and then kind of reply once I see the question. All right, so with that, let's get started with image level tasks. And so for those of you who are familiar with sort of this standard setup of machine learning, image level tasks are going to be the tasks that are closest to sort of standard machine learning. And so image level tasks are really kind of answering sort of the fundamental questions of what is going on in this image as a whole. And they can cover semantic information. That semantic information might be sort of what's going on in the image as a whole in the sense of kind of just classifying that image. In this case, classification might just mean that this is an image of a scooter. it might mean that this is an image of a person, and so on. Now, classification is kind of special because it only assigns the most dominant label to the image itself. So you're looking at this entire image with all sorts of different things going on in it, and you're assigning it one single label. That's just some semantic label. Now, a bit more detailed is tagging, where instead of assigning just a single label, you're now going in and trying to enumerate all the possible things that are going on in this image. And so if you look at tagging, you might say that there is definitely a person. Sorry, you cannot see this here very well. Let me try to write it here. Maybe there is a sidewalk. There might also be signs. If you know Mossburger, you might have Mossburger. I'm not even sure if it has 1 or 2 S, and so on. And so tagging really is the problem of trying to come out with all possible categories this might fit in. And so the difference between classification and tagging is classification assigns one label, tagging just tries to sort of assign a group of labels to the image. And then finally, we have image retrieval, which goes a step further than tagging, which essentially says, kind of describe this picture in the most compact form and find me other pictures that look exactly like this one, right? And now you might think, for example, tagging and classification, they might be used in Google image search. If you search for an image, Google might use a classification model or a tagging model to retrieve relevant information. In reality, Google actually uses a lot of text information to retrieve images, but that's sort of besides this lecture here. Now for retrieval, this is the equivalent of you uploading a picture to Google and looking at sort of the visual image search that Google has. Now, another set of tasks that you might be interested in that are image level are sort of the location or where tasks. The easiest one here is figuring out what sort of scene this is. This is clearly a scene of a sidewalk. Maybe you would want to say it's in a city. And it's, again, just sort of a classification problem. But instead of looking at the semantics, you now look at the location. Question, do we have a handout for this lecture? Sorry, I forgot to give the handouts to the organizers. I'll get it to you after the lecture. All right, so the next sort of question you might be interested in is what region was this captured in? There's also a question, is there a difference between tagging and multi-label classification? There is no difference between tagging and multi-label classification. The way tagging is solved is through a binary classification problem over all the possible tags. And we can get to that in a moment. All right, let's get back to the location tasks. Another task that you might be interested in is what region was this captured? Now, this picture here was captured in Taipei. That might be sort of the general region. You want to also just say this is a picture from Asia. And again, this is a classification problem. And then the final problem, or like the final granularity of this, is trying to figure out where exactly was this picture taken. And that would essentially mean kind of figuring out the exact geographic location where this picture was taken. It turns out this actually, it seems like an incredibly hard task, but computer vision systems can do this quite reliably if you stay within sort of large cities and areas that have been seen before. All right. Now, the next sort of image level tasks that people study are sort of context related tasks, where we're looking at sort of not what's in the picture, what can you sort of say about the picture. One such interesting task is what year was a certain picture taken at? And in modern pictures, you can read this off metadata, but in older pictures, you actually have to look at the camera quality or sort of the pixel level detail to figure this out. Again, what time was this taken? Maybe what season was it taken? Or even you can even infer what camera a certain picture was taken from. And turns out there's only about 12 different types of cameras people take pictures with, because there's only about 12 different manufacturers of the chips. And so you can infer which manufacturer a picture came from. Then you can also infer sort of who is in the picture. This is often done through celebrities. There's large data sets of celebrities, and you can sort of classify who is in this picture. Now, if you take this a step further, you can go beyond celebrities, and you could even infer sort of an identity for each person in this picture. And this is called re-identification. Now, in recent years, this has found many sort of negative applications in terms of surveillance. It's also not that actively studied in computer vision anymore because of this. But it's definitely a problem that people looked at quite a lot. And then finally, there is one interesting class of things to image level tasks, which is anomalies. And this is, for example, detecting danger. Looking at an image and saying, is there something dangerous in it? Is there any illegal activity going on in this picture, right? Is there violence or adult content that you should not show to children? Google, for example, does this very well. In their image search, they will have a filter that filters out any sort of violent content so that you're not exposed to it. And then finally, detecting fake news is another, or fake imagery is another big image level task. Now, this might have sounded like a gigantic list of different tasks, but the nice thing about all of these tasks is they all have exactly the same structure. And the structure is that we go, look at an image, and we essentially predict one output. If you think of this in terms of machine learning, all we're doing here for all of these tasks is we're going to learn some function f that maps the image, which I'll call x here, to some output y. And it's even nicer than this. For all of these tasks, sort of the domain or the structure of x is going to be exactly the same. The only thing that changes is what output label or what output label space we associate with the images, right? And so in terms of outputs, there's about 3 major groups of outputs that we produce using sort of this deep learning or function approximation. The first one is classification outputs. And that's definitely the semantic classification. Tagging is part of this. Scene classification, even region classification might be part of it. If you want to figure out what camera picture was taken off, that's a classification problem. Figuring out if there is a specific celebrity in the picture, that's classification. Danger, illegal activities, or violent content can also be phrased as classification. Then there are a few regression problems. Geolocalization is one, trying to figure out where in the world was a picture taken, trying to infer what year, time, or season was it taken. Now for season, it could also be classification here. It can really be both. And then there is 2 sort of problems that don't fit in either classification or in regression, which is retrieval and re-identification. And here we're really trying to figure out what is the similarity between different images. And so if you're familiar with a lot of the machine learning literature, you can see that kind of most of computer vision, like this chunk here, nicely reduces to very simple machine learning problems. There's 2 that reduce to embedding learning, and then there's fake news detection, which can be classification, but oftentimes it's actually solved in a slightly different manner by kind of trying to detect outliers. All right. And so the three sort of big problems we're going to look at today is image classification. And here we separate into binary classification, which might be tagging or sort of figuring out if there's adult content or not. These are binary problems. And it might be multi-class, which is image classification, scene classification, and so on. Then we have regression problems, where we're trying to output not a class or a binary decision, but instead try to output a floating point value and try to regress to something. And then we have embedding learning, where we're trying to find some sort of distance metric. And the way we're going to do this is by outputting a feature vector and then just looking at Euclidean or cosine distances between these feature vectors to tell us if two images are closer. So these are the three problems we're going to look at. Now, the nice thing about computer vision is it's actually even a little bit simpler than studying three different problems, because all of these problems use sort of the exact same structure. So you might have about 100 different image level tasks. Almost all of them use the same sort of setup, which is we take an image, we feed it through a deep network, and then we produce an output. Now, in order to train this deep network, we're gonna collect a large data set of images with corresponding labels, and we're gonna train the network to output the labels that correspond to those images. Right? Before I'm going to go through the details on how we're going to train this, there is a question in the chat, which I'll quickly get to. I think fake content could be classification. Yes, fake content could be classification. It is not always solved as classification, just because there's way more ways to create fake content than there is ways to sort of, there's training data that you have to train your classifier. And we can get to this in the discussion if you would like. All right. So let's get back into the image level tasks. And so really, the way we're going to do these tasks is we're going to take a data set of images with corresponding ground truth labels. Then we're going to set up a network. Just here. We're going to define a loss function that essentially tells us how different is the output that the network produced from what we expected from our data set. All of these steps, the loss function and the network, are nicely differentiable if we set it up using deep networks. So we can just use gradient descent, stochastic gradient descent, and large amounts of data to train the weights of the network. So we're going to train the weights of the network so that the outputs here match the labels that we have, right? Now there's three things that you can really vary in this setup here. The first thing is sort of what network do you choose? So that's the sort of the first decision we need to make. Then the second thing is what losses do we use? And the third thing is what data do we use? Right? And we'll look through each one of them in detail. Now there is a question. Adversarial attack also considered as an image level task. Yes, it is considered as an image level task. I left it out primarily because I don't think it actually is necessarily a recognition or in many ways, it's not computer vision. It's making the models more robust. It's definitely a discipline in computer vision, but it's not necessarily a task. Like you rarely get up and really want to attack an image. And so that's why I left it out. And we can, again, talk about adversarial attacks in the break if you'd like, and I'm happy to answer questions about them. All right, now let's get back to the slides here. And so the first thing we're going to look at is what networks did people use, or do people use, to analyze these images. And by far, kind of the most successful network, or the classical example of a successful deep network in computer vision, is Lexnet. It's by now almost 10 years old. And it's sort of a very interestingly engineered network. It first resizes all images to a fixed size of 227 by 227, and then it sort of repeats convolutional layers, which is just running a bunch of convolutions over the image. Here with a fairly large kernel of 11 by 11. Then it uses some pooling, some more convolutions, pooling, convolutions, pooling, convolutions, pool. All right, and so this structure was really motivated by much earlier work on Lexnet, where convolutions are sort of there to build up feature representations, and then pooling is there to reduce the size of the feature representations. And this is visualized here. So what Lexnet does internally is it looks at the image, and then it builds these maps of different features of the image itself. And as you go through the network itself, the spatial resolution of these maps gets smaller and smaller, but there's going to be way more channels in the image. And so you can think of, you get a lower and lower resolution representation of the image, but it gets more and more abstract and higher dimensional. And so in the end of Lexnet, there's also a couple of special layers that are sort of no longer used nowadays, which is there is a layer that flattens everything into a fixed size feature representation, and then it goes through a couple of linear or MLP layers. And so Lexnet is really kind of sort of the one big success story in deep learning and computer vision. And it won the Imagenet competition in 2012. And it really it ensured that within half a year, almost all serious computer vision researchers were sort of transitioning to deep learning. And the reason for this is that it really won the competition by a gigantic margin. Before 2012, it looked like computer vision was sort of plateauing, and we wouldn't be able to solve image classification, at least at the level that we wanted to. And Lexnet really came in and showed there's this huge gap if you just switch to deep learning. And then that gap started to close more and more over the remaining years. Now in the later years, there's always been sort of one very nice and pretty architecture every year. I'm not going to go into all the details in all of these architectures. But I'll show you the next sort of big architecture, which is residual networks. And the big change that residual networks brought was, instead of trying to model everything as convolutions and having the image sort of pass through the network sequentially, now we parameterize everything as residuals to convolution, or we parameterize, or we use the convolutions to compute residuals to the image itself. And so there is connections in the network that just skip entire blocks of convolutions. And what the convolutions now do is they sort of parameterize, instead of parameterizing a function f of x, they now parameterize g of x, which is, sorry, where f of x is x plus g of x. So this part here is g of x. And instead of parameterizing the function directly, we now just parameterize identity plus that function. Now, you might think, okay, well, there's nothing to this. This is just some simple mathematical trick. So why is our residual nets special? The main reason why the residual networks are special is because they allow you to train much deeper networks. Because if you use gradient descent to train a network, if the gradient goes through too many layers, it will sort of be diluted. But if you have a residual network, you always have part of the gradient go through the residual connection, which makes sure that you can have a gradient that comes from your loss function to any layer in the network, and you will not be too diluted. Now, there's many different variants of residual networks. Okay, there's also, okay, before we go into the variants, what can you say between Lexnet and VGG16? Yes, in my view, VGG16 is a very nice version of a big Lexnet. And they actually had to introduce quite a few tricks to make VGG sort of scale to the size it was. So VGG could scale to about 18 to 20 layers. And with the residual connections, they could now go and scale it to up to 1,000 layers, which is deeper than anything that we would need right now. There's also gradient vanish. Yes, gradients vanish. It's not necessarily that they actually go away, the gradients. It's just that they get sort of multiplied with random matrices too often. And so once you multiply a gradient with a random matrix often enough, it's just going to be a random number and you're not going to learn much. Gradients completely going away or completely vanishing, batch normalization should actually take care of this. All right. I'll monitor for some more questions, but in the meantime, I'll just cruise on. So yeah, residual networks really came in multiple different variants. The smallest ones were about 18 layers, and these are similar to sort of larger Lexnet architectures. They would have been trainable without residual connections. They just worked better with residual connections. But then going to like 34 or more layers, you really need these residual connections so that the gradient can go backwards and sort of supervise early layers in the network using the loss you have down here. Now, the other sort of special design choice that residual networks made was, in the end, they did not have fully connected layers anymore. They had sort of just one average pooling layer, which means that you can run the network sort of fully convolutionally over the entire image, and then you just look at all the outputs the network gives you and you average it together. And so that's sort of a nice introduction that actually came much earlier. It's Network in Network that first did this, and then Googlenet really picked up on this. But residual networks also feature that sort of average pooling in the end, which really helped them sort of go to a much wider set of tasks in computer vision. Okay, there's another question in the chat, which is, what situation can we consider between average and max pooling? Okay, yeah, let me go back to this. You'll notice that here inside of the network, there's no more pooling. In the beginning, there is a max pooling here, which it's actually not clear if you actually need the max pooling or if you can get away without it. But inside of the network, people usually don't pool anymore. This entire philosophy that you pool to reduce the feature dimension, that has gone. Now, to reduce the feature dimension, you can actually just stride a convolution, which means you don't evaluate the convolutional kernel at every single point, but you instead skip some elements in the convolutions. All right, and then in the end, the average pooling in the end here is actually not necessarily an average pooling kernel. It's just averaging all outputs together. Yeah. All right. Now the next thing we'll look at is sort of what loss functions do we use to train these networks. So now we have a definition of a network, but how do we go about training them? And the first problem we look at is classification. where we want to know, well, is this a picture of a dog, a cat, a pony, and so on. And so the very first thing we need to do is we need to figure out what should the network output. And oftentimes for classification, you just want to output sort of the probability of this image being a cat, the probability of it being a pony or a dog or whatsoever. Actually, you want to output the log probability. And then the loss function should just be maximizing the log probability of the ground truth class. And if you do this right, what will happen is that the probability of the ground truth class will go up during training. And because if you phrase as a classification problem, probabilities are normalized, the probabilities for all other classes will go down. Now, if you phrase this as a binary classification problem, which would be sort of, is this P cat or not? Then you would have to have a loss for every single output, saying this is not a dog, this is not a pony. And so that's how you would do binary classification. And again, this is more or less standard machine learning. Computer vision really didn't invent anything. The same for regression. If you would want to regress to a continuous output, again, we would just you would use an L1 or an L2 distance. Again, standard machine learning. Okay. Now, the final loss function that is a little bit special to computer vision are embeddings. Okay, actually by now embeddings are also used all over natural language processing. But in the early days, it was at least somewhat special to computer vision. And so here, the goal is to output a feature vector. Instead of outputting a different class or a different sort of continuous value for each image, you now just output a continuous feature vector. And this really is going to be some sort of feature y in real numbers in some dimension, right? And you want to output this feature vector such that features from the same class or from the same sort of instance or whatever you want to classify are the same, but features from different classes are different, right? And the classical way to do this is to use what is known as a metric learning, or like most commonly a triplet loss, where you say that you want to embed some features in a metric space. And now the loss function is saying that for any pair of positives, there should be no negative that's closer than the pair of positives as to one another. And that is the triplet loss. You can write it down mathematically as simply just saying that you want to maximize, or you want to minimize sort of distance between, let's say this is A, B, and C. So the distance between A and B should be smaller than the distance between B and C. Now this, you cannot optimize this directly in a loss, but you can convert this to a loss by simply just saying that you want to minimize the maximum of A minus B minus B minus B minus C. Right? And so this will ensure that if you enumerate all triplets A, B, and C, that A and B are going to be smaller, oh, sorry, the max between this and 0. The distance between A and B is going to be smaller than the distance between B and C. Right? I hope I did the sign right here. Now, a much simpler way to get to the same sort of goal is to actually phrase this secretly as a classification problem. And you can phrase this secretly as a classification problem by essentially saying that everything that you want to group together in a triplet loss, you're going to assign it one ID or one feature vector. So if the goal here is to get an embedding for cats, you can just classify these as cats using a classification loss like a log likelihood or log softmax. And that will pull these features together. And now you classify everything that's, for example, that you want to embed as a dog as the dog class. So you could essentially say that this is going to be P cat, this is going to be P dog. Now you can do this on a class level, and then you will get an embedding that sort of groups different classes together, but you can also do this on an instance level. So you can say that you want to classify that this here is P, like this specific black cat. This here is gray cat. This down here is the white dog. And if you optimize or if you learn this classification problem, just to identify individual instances, you will learn an embedding that is specific to an instance or to a specific kind of identity in an image. All right, there is a few questions in the chat, which I'll get to. Is there any need to consider there? Yeah, so the question is there any need to consider variable input sizes? And for image level tasks, strictly speaking, there is not. For later tasks in computer vision, the input size actually becomes a huge issue. And if you look at sort of dense or sparse tasks, there the input size really matters. And there's no longer going to be a fixed input size for all images. The absolute value or the norm. It is the norm. You can use an L1 or an L2 norm. It really doesn't matter that much. If we have more than 3 features, what would the algorithm be? Yes, in this case, if you would have more than 3 features, you would essentially have for every sort of embedding, for everything that you want to pull together, you would have one specific class. And so if you think of doing this, for example, to find an embedding of people or faces, for every person, you would have one specific class. So you would have a Philipp classifier, then you would have Professor Lee classifier, you would have whatever other classifier. And if you train these classifiers, you would then get sort of a feature or an embedding that's specific to individuals. And it turns out that that embedding or feature actually generalizes to new individuals that you did not have in your training set. All right. Now, the final part we're going to talk about here is data. And really the only reason why deep learning didn't work as well as it did in 2012 earlier than this is because people never tried to run it on gigantic data sets. And so the largest data set that people often train on is Imagenet. It has 1,000 classes. It actually has 21,000 classes, but 1,000 classes are commonly used to train. That's 1.2 million images. It is very well created. It's very well balanced. So almost every class has the same number of images, and it's very nice, simple images. It's just an image of one object. And so that's the sort of the gold standard data set that people train on. Now, if you would take your deep network and train it on just these images, what you would see is that the network is going to completely overfit. it's going to work extremely well on the training images, and it's not going to generalize at all to testing images. Well, I wouldn't say at all, but it's not going to generalize very well to testing images. And it's not going to perform nearly as well as models that we had pre-deep learning. And the main reason for this is that deep learning models are actually very large, and 1.2 million images is not that much. And so what we need to do during training is we cannot just use the training data as is, but we need to sort of try to create more data on the fly. And so this is often called data augmentation. The simplest forms of data augmentation are just flipping an image left, right. It might be cropping an image to a slightly different location or changing its color. And note that if we just change the way the image is cropped or slightly change the color, the content of the image doesn't drastically change. So all of these sort of augmented images have still the same label here. So these are all still images of dogs. And that's exactly kind of the main kind of driving force behind why deep networks don't overfit and why they work so well in practice. It's the ability of kind of data augmentation to take one image and make millions of different sort of slight variations out of it so that the network will never see it as the same image twice and it will not overfit. Now, there's also sort of slightly different, more elaborate data augmentations, and some of them are super weird and should not work. One of them, for example, is Mixup, which is you can take two images and just overlay one over the other. And let's say you use transparency and you put a 30% transparent dog or a third transparent dog on top of a cat image. Now you ask the classifier to predict that this is a third dog and 2/3 cat. And so this data augmentation gives you about a point or two improvement on Imagenet if you just mix these images. Now, a slightly less weird way of doing this is instead of just blending the two images, you can copy one image on top of the other. And then again, depending on what the area the two images occupy, you can just say this is like half cat, half dog. And so what this will do inside of the network, it will just make it sort of robust to kind of a wider range of weird images. Now, you would never see this image at testing, but this image might be closer to a new dog that you have not seen in your training images. And so that's why this works. Okay, we'll get to some questions. If we have more than three features, what would how do we answer this? How are outliers handled for multiple features and what algorithm can be used? Sorry, I don't get the question. Can you just give me, can you give me some more context and then I'll answer the question. Finally, I have empirically seen Mixup work for tabular data as well. Yes, it is super strange that Mixup works. Yes, I'm glad it also works for tabular data. Can you please say more about data augmentation on the fly? Yes. So data augmentation is done sort of as you train. So you will never see the same image twice. Every time you load an image from your database, it is augmented in a slightly different way. This is actually quite important. If you would run data augmentation over your dataset once, you would still overfit to the dataset. You would just overfit to the augmented dataset. And so every time you load a new image, you do change it directly after you load it. And so that's how it's done on the fly. Okay. In the interest of time, I'll move on and then we'll have a bit more of a discussion later. All right. So I hope I was able to show you that sort of, even though there's this gigantic zoo of sort of different image level tasks, all of them sort of share the same sort of recipe. Now, in the last few minutes, we'll now go in and look at sort of what are exciting opportunities for you to go and contribute. And one area is definitely in architectures for these image level classification problems. And I would say from about 2015 to 2020, we were in a sort of weird space when it came to coming up with new architectures for classification problems. And that is because it was all sort of improvements of residual networks. There was not this one overarching new idea that came in and disrupted everything. Residual networks came in and they really caught us a little bit off guard. And after about half a year, everybody was using residual networks. In 2020, and even nowadays, people still use residual networks as part of their toolbox. And so what happened in this range between 2015 to 2020 is there was lots of tuning and nice small improvements over residual networks. And then there was lots of work in neural architecture search, which was an automated way to find sort of improvements over these architectures. The one thing that came out of this is very nice, efficient models, models that use fewer energy and are much faster. Now, in 2020, something very, very interesting happened, which is sort of convolutions fell a little bit out of favor. And it really happened with the paper that I cited down here, the first, which is an image is worth as 16 by 16 words, which showed that you can take an image and cut it up into 16 by 16 patches, and then feed that to a language model, just a standard transformer, and that language model is able to interpret the image. Now, this only works if you train it at a gigantic scale with the resources of, in this case, Google. But that really showed that there's nothing magical about convolutions. And since then, there has been a very strong movement away from convolutional networks and kind of exploring alternatives. One of these alternatives has really been sort of vision transformers, which is language models, transformer-based language models. There's sort of hybrids between transformers and convolutional networks, which is sliding window transformers, where we put the language model inside of a sliding window and then just change the way we place these windows. And so they still use sort of the structure of convolutional networks, but they use a transformer as the internal kind of engine or building block of the model. There's also been some work just a few months ago that showed that you might not even need a transformer. You can actually do almost as well if you just replace everything with multi-layer perceptrons. So you can have sort of sliding multi-layer perceptrons or not sliding multi-layer perceptrons, just multi-layer perceptrons on patches. If you do the interactions between the features and the patches right, you can get away by having almost all multi-layer perceptrons in there. And so this is sort of a very active area, and it really kind of created a lot of excitement and also a strong boost in many of the vision tasks by kind of moving away from this local optima of convolutions and trying to explore like more creative architectures. Now, the other very active area in the classification or image level tasks has been self-training and self-supervision. And so what self-training does is it says, well, maybe we shouldn't just train on the labeled images that we have. Maybe we can use additional unlabeled images to improve the model that we have. And a popular theme there is to essentially say that, well, maybe you can use a clean image to go supervise the network of augmented image. So maybe you can have a loss and say, okay, I'll use the clean image to assign a label to an image that was on that somewhere from the internet that the human hasn't labeled. And now I'm going to use that clean label to supervise augmented version of the same image. And so here you're really using data augmentation to help boost the model's performance on images that you haven't seen. And it turns out you can do a very similar trick without ever learning about labels. You can just learn a model that is able to sort of identify an image by its embedding, and then just reproduce that embedding on an augmented version of that image. Just saying that two augmented versions of that image should embed to the same space, to the same point in space, and two different images should embed to different points in space. And that training objective, it turns out, can get very close to large labeled collections if you just consider image level labels. All right. So this is sort of the end of the first part here. I think I already went over a little bit, but we'll just see how much time we'll use for the rest. And so in this first part, we really looked at sort of looking at an image. What can we say about this image on a global level? What labels can we assign to the image from kind of a global level? And this is very much just sort of standard classification, as you know, from machine learning. I'll now go through some more questions, and we'll have maybe about a 5-minute break to try to catch up with the schedule. And it's not too weird. I think that's the best explanation I can give you. Are autoencoders or variational autoencoders examples of models that use self-training or self-supervision? Yes, they were early examples. They don't lead to very good feature representation in computer vision right now. So you cannot use an autoencoder to train a ResNet, for example. I mean, you can, but it's not going to give you a very good representation. These sort of the representations that use embeddings and augmentation work much better nowadays. How can I train a state-of-the-art model, for example, YOLO, on a new object that I've never seen before? We'll get to this later. This is actually one of the open problems. Very good question. With the presence of generative models, why do we need data augmentation? It's a very valid question. I think it's very hard to make the generative model indistinguishable from real images. And it's in part has to do with the fact that if you look at a generative model, the way you generate the image is also through convolutions. And so if you then use a convolutional network to learn some sort of representation, what will happen is that the filters in the convolutional network that you learn for recognition will sort of mimic the filters that you use to produce the content. And so that sort of mimicking sort of causes some slight overfitting. And so it has been quite hard to make generative models produce sort of new content that it can use to train. Yeah, we'll get to object detection later. Why do people not use the Fourier transform to get sort of like wavelet-like features? I think really the answer is because it didn't work that well. So convolutions themselves, like if the kernel is large enough, you can use an FFT to evaluate the convolution very efficiently. But the convolution itself already gets most of the sort of spatial structure out of the image without the need to actually go into the Fourier data. Okay, the other question, is there active research at the intersection of causality and computer vision to improve generalization? Yes, there is, in the sense that people reason about physics from visual data. That's part of the causality research. I think the main reason why we haven't really gotten to causality in recognition is that we're just nowhere close to getting the inputs to any causal model right. Yeah. All right. Last question I'll answer is, are most augmentation techniques cheaper computationally than generative models? Yes. Is it any significant advantage? Probably yes. Now, you could just generate a larger data set ahead of time, but then you would still have to combine it with data augmentation most likely. All right. All right. So let's move on to the second part of today's lecture, which is looking at tasks that don't give you a global answer per image, but that go in and give you a very detailed answer about individual parts of an image or a video. So one of the tasks that we're going to look at here was already mentioned before, which is semantic segmentation. And the goal really here is to sort of say for every single pixel in the image, what class does the object or the thing under that pixel have? And so here, this class might be, if you're in a driving data set, it might be sidewalk. In other data sets, this might just be ground. If you're interested in material classification, this might be, I don't know, stone or whatever material this is. Then here, this could be building or wall. This is again building. Here, this would be this. You could classify this as vehicle. Up here is person. Here more person, and so on. And so this is a way to go look at an image and just trying to sort of globally parse it in a very nicely structured way. Another way to sort of look at semantics is affordances. And instead of looking at the semantic class here, you look at what can you do with an object. And you could, for example, think of this is all drivable area. I don't necessarily care what it's called as long as I can ride my bike or my scooter on. Now, the next task, next set of tasks we're going to look at is geometric, which is you can infer either from one image or from a pair of images, sort of how far away a certain point is from the camera. You can also figure out sort of the local geometry by looking at what is the normal direction. So what is the direction that's normal, that's orthogonal to the surface at every single point. And then you can, once you have these two clues, you could even infer sort of what is the lighting condition at every single point in the scene. And you can separate sort of what is the surface color from what color is caused by lighting. And this is called intrinsic image decomposition. Then the next set of sort of tasks is more sort of visual or image characteristics, which is what are sort of the prominent parts of an image, which you can think of. You can have a heat map that just tells you, hey, if you would have to look at one thing in the image, what would you have to look at first? And that is image saliency. And then you can extend this to not just look at the one prominent thing, but you could look at sort of, if you looked at everything, what are the things that visually are sort of nice and pleasant for you to look at, and what are the things that are sort of off-putting? And this is often used in video compression to figure out which part of a video can you compress more and which parts can you compress less. And this is, for example, a way that Netflix uses to greatly reduce sort of the amount of bits they need to transmit to you. They run sort of quality of experience on a large video and then figure out, hey, this might be a dark scene, you don't see much. I can compress this a lot. But then on the other hand, if it's like some nice, beautiful still image where you would see compression artifacts immediately, they will compress this less. And then finally, I think a very popular sort of dense task is image generation. And we're just going to look at two here, which is super resolution and image compression. And we're going to look at these two because they fit in sort of the nice framework of dense tasks, which is we're starting out with an image. And what we want to produce here is sort of an output of the same size as the image. But now each pixel here is sort of associated with either a classification output, with some sort of regression target, with a color value that you want to produce. And so really here, we again learn a mapping from X to Y. The only difference here is that Y is now, if X was sort of width by height by 3, Y, the output is now also width by height by some other dimension, right? So now the input is dense and the output is dense. And again, you can classify dense tasks in sort of actually just two different groups, classification and regression problems. And so semantic segmentation, that's a classical sort of classification task. If you look at saliency, well, saliency somewhat, quality of experience somewhat, these are also, can be phrased as classification tasks. Depth, normals, and intrinsics are classical regression tasks. You can regress to quality of experience if you have non-binary data. The same as you can sort of regress to saliency if you have non-binary data. Super resolution and compression are definitely regression tasks. And affordances can again be either binary, if you just want to know is this drivable or not drivable, or it can be continuous if you want to estimate how drivable something is. What about visual attention, categorized under what? Saliency is usually is another word for visual attention. So if you want to compute an attention map of what people look at, this is usually referred to as saliency. And so if we want to go from image level classification to dense classification or dense tasks, all we do is we essentially swap out a network that now produces a dense output, and we swap out the data set that now has sort of dense labels. If you would want to say segment this cat, the data set would now just have a segmentation map in there, and the output here would also be a segmentation. Now, the one thing that we actually don't switch out is the loss function. We can use exactly the same loss functions for image level tasks and dense tasks. And so the two things we're going to look at here is what are networks that produce dense outputs, and sort of how do we train these networks on the data that we have. Now, the easiest way to sort of produce a dense output is to reduce it to a standard classification problem. So one way to do this is to say, I'm going to look at a patch in the image, and now I'm going to classify the central pixel in that patch using a classification network. And now I'm going to move over a little bit, look at an overlapping patch, and I'm going to classify the next pixel. All right? I'm just going to run lots and lots and lots and lots of classifications, and that will give me a dense output. I can do the same thing with a regression network. I can run lots and lots and lots of regressions and get a dense regression output. All right? Now, this is obviously horrendously slow, and nobody will ever do this. But what you can do is you can mimic this using a convolutional network. And you can run a convolutional network sort of in a sliding window fashion over the entire image and get as an output a dense segmentation or regression. All right? For regression tasks, I often see binning or discretization, and this often helps in the conversion of the model, probably because it reduces noise. Yes, there's many ways to phrase regression, and you're right. So the question was that oftentimes you can bin regression tasks and treat them as classifications, and that gives you a better outcome. There's many sort of variations of how you how you mix classification and regression, and I can give you some pointers after the class if you want. I think this is going to be a little bit beyond the scope of what we're going to talk about today. But there is some nice geolocalization work that actually nicely combines this binning with the regression. We consider human pose estimation by stacked hourglass nets as an example of a dense task. No. I put it as sparse, and we'll get to sparse tasks later. Right, but now let's go back into sort of how do we do this dense classification efficiently. And so what we can do is we can take a residual network that we used before, and we'll just look at it. And so if you look at the residual network and go sort of from the top to the bottom, you'll notice that sort of all of these operations here are just either convolution or some pooling with a fixed kernel size. And all of these operations kind of slide over the window itself. So each one of these operations will look at the image and produce another image just with more channels, and maybe sometimes at a slightly lower resolution. And this goes down all the way to the end here, all the way here, where the output is going to be some, I think it's might be, depending on the input resolution, it might be some 7x7 output map that has about 512 different channels. All right. Now, if you look at this, you can just make the image slightly larger on one side. And what will happen is this activation map here will get slightly larger. And so what we could do is we can just, instead of classifying every single patch, we can now just feed in a larger image, get a larger activation map, and then regress to the output from that activation map, right? And that's how fully convolutional networks do dense classification. Now, the only catch here is that if you look at the structure of the network, the resolution of the original image is reduced. It's reduced by a factor of about 16 to 32, depending on the network architecture. If you want to get a classification output for every single pixel, you need to get this resolution back. And there's two ways to do this. You can either just use linear interpolation, just upsample it like you would upsample an image, or you could have sort of transpose convolution or up-convolutional layers, which kind of expand the feature map, right? But this allows you to take the residual network and now make it so that you can run it over an image and get a dense output, all right? And so this part here is now done, right? We now have a network that can take an image and produce a dense output. The only thing that's left is trying to figure out how do you actually train this network. Loss functions are the same. The data itself is not, right? So the data sets for dense classification are relatively limited. There's about 4 or 5 very large ones. One of them is Microsoft Coco that has dense segmentations for all objects, and then also for certain background categories or certain stuff categories, for example, the grass here. All right. There is cityscapes or mapillary, which are mainly driving data sets, which have very fine-grained annotations for very high resolution images. Now, just to give you some context, creating one of these high resolution annotations takes about 1.5 hours. Okay, so you can imagine if you actually, and 1.5 hours for somebody who's actually reasonably skilled and trained. And so you can imagine you cannot scale this to very, very large data sets. And so that's really sort of the biggest first issue that semantic segmentation or these dense tasks face, that there is not a lot of data available. And so you kind of have to make a choice between, do I want to train on a small, very well annotated data set, or do I want to train on a much larger but slightly noisy data set? And neither of which is a very good trade-off. So one solution to this is to actually not train on these dense tasks first, but to instead train on an image classification for which we have very large data sets, and then use that network and just make it fully convolutional. And what that means is that you just copy over all the weights from your classification network and just reuse them when you run the network fully convolution, right? And so that has been sort of the first and very successful approach of getting dense classification or dense regression to work. Okay, are we doing 3D convolutions in dense classification? Okay, what would the third dimension be? So it is possible to have 3D convolutions in dense classification for videos. For images, I wouldn't know what the third dimension of the convolution would be. Is there a reason for using odd number of size of windows for conv layers? Yes, there is. Okay, yeah, I'll explain. So if you would, let's say, if you look at a convolution that's 3 by 3, there is sort of a correspondence between the center of this convolution and one of the pixels. If you do 2 by 2, there is no such correspondence. So the center of the convolution will fall between pixels. And what happens if you convolve an image with a 3 by 3 kernel, it will stay the image at the same location. If you convolve it with a 2 by 2 kernel or 4 by 4, it will shift by half a pixel. And a lot of people are a little bit OCD about this shift and don't like it. And that's why we always use odd numbers. Does dense here really mean that the output of is a matrix of dimension 2 or above? Yeah, so that means what dense means is that the output is of the same size or roughly the same size as the input is. And yes, it's going to be a matrix of dimension 2 if you only have one value regressing to. It can be more. It can be dimension 3 if you, for example, do classification. All right. Let's get back to our solutions. Now, the second solution that does not use pre-training is to use simulated data. And so there's many ways you can get very accurate dense annotations from graphics engines, from simulators. That can either be if you have your own game engine that you work with, or you can even kind of hack into existing game engines to extract ground truth labels for these vision tasks. And these ground truth labels are going to be perfectly accurate, and they're going to be extremely detailed. Now, the only issue with this is that you need to be able to use these ground truth labels in the end for real images. And so there's a slight gap between sort of images you see in video games here and the images you would expect in the real world. And the hardest challenge actually has been trying to kind of bridging that gap. It turns out it's much easier to transfer between different data sets of real images than to go from sort of a video game to the real world. And this is still a very open and active research area, and it's called domain adaptation. Right. Now, another way to go to sort of solve the problem of small data sets is instead of just trying to use one data set, and is to use all the data sets that you have for a specific problem. And this has been quite successful in semantic segmentation and in depth estimation. And here, really the goal here is to just collect all the data sets that people ever collected that, for example, do monocular depth estimation, which is trying to figure out how far a certain pixel is from the camera from just a still image, and combining them into a large data set. Or you can do the same thing with semantic labels, and you can combine them into one common data set. Now, this sounds quite easy and trivial. It actually turns out there's a lot of little sort of research and engineering nuggets all around this problem. And it really has to do with the fact that different data sets use different annotations. And they use different, if you collect human annotations, they use different instructions to different people that, that sort of annotate the images differently. And so within one data set, the images are annotated consistently, but between different data sets, they're not. And so the kind of sort of interesting research problem is it possible to just take these separate data sets and just automatically kind of fuse and combine them? Now, the two first attempts to this have been by large manual. So there is a data set called MSEG, which combines lots of different semantic segmentation data sets. And what they did is they spent about half a year trying to sort of come up with a common taxonomy and clean up individual data sets to match that common taxonomy. But that has shown to be extremely successful in getting sort of better semantic segmentation models. Now, obviously, the question is, if now somebody creates like 5, 6 more data sets, can you start to merge these data sets automatically, or do you always have to go do the manual labor? And then the other sort of success story in this regard has been molecular depth estimation, where individual sort of data sets have always kind of been known to overfit drastically to sort of the individual domains that were captured in. And so what sort of the first citation down there did is they just combined all of these molecular depth estimation data sets into one data set. And here, the unification is not as hard as trying to unify different concepts. It's just trying to unify different camera models or different sort of internal camera parameters that would lead to different relative depth estimates. And then finally, there's also sort of the question, if the data sets that you train on don't have a single model that works best on them, is it possible to sort of still train on multiple data sets and get as accurate as possible on these multiple data sets? And so the main challenge there is really just different setups, different architectures, different sort of best practices that exist across different data sets, and no single one will work on all. It's more of an engineering question, right? So that's kind of sort of the open research problem number one in this area. Now, the second open research problem here is really sort of image generation in a very specific setting, which is compression. And it's open for many reasons. It's currently studied by a fairly small group of people. There's only about, I would say, 20 to 50 researchers in the world that study sort of image compression using deep learning or using machine learning. But it is an extremely important problem. And it's probably one of the sort of most important dense regression problems if you care about sort of global impact. And the reason for this is that about 10%, at least in the US, about 10% of the energy that we produce in the US is used to power the internet one way or another. And believe it or not, 80% of the traffic that the internet produces is images or videos. Now, that doesn't mean that 80% of that 10% is going to go towards streaming videos, but a large fraction of that is definitely a large fraction of the power consumption of the United States is just that people can watch videos or look at pictures online. Okay. And so if you're interested, there's a nice citation down there. There's also some critique work that shows that this might not be the worst thing, because a lot of the data centers that power the internet actually use, at least in the US, use green energy just for sort of image, because companies don't want to look bad. But it still kind of occupies a gigantic chunk of the internet and the global energy use. And so any percent with which you can make sort of these images smaller, any percent you can make the encoding and decoding of these images and videos more efficient is really going to give you a huge sort of delta if you look at the cost of running the internet and also the environmental impact. And so besides that, image compression is also a very fun topic. And so there's really two ways people have tackled image compression before, which is, one is sort of the standard autoencoder, where you're trying to learn an autoencoder that takes an image and reproduces that image, but in between uses just a few bits. Now, the challenging part here, or the big research question really here, is how do you produce these few bits? And how do you produce them sort of in a differentiable way, so they can use a gradient to train both encoder and decoder of the autoencoder, but also sort of in a binarized way so you can easily compress it. All right. There's many ways to do this. There's many nice mathematical ways to sort of use entropy coding, which is sort of a mathematical or an arithmetic way to translate probabilities into sort of compressed codes. How to combine this entropy coding with sort of an encoder, decoder, or an autoencoder architecture. But sort of the exact structure of the architecture, sort of also the way you produce these codes, all of this is still completely open. And if you're into machine learning, this is a very fun topic to study because it has a lot of math in it, a lot of learning in it, and it has a huge practical impact. The easy version of this problem is going to be studying it for images. The really hard version of this is to study it for videos. Because in videos, you have a lot more repeating structures that you would need to compress together, and a simple autoencoder structure is not gonna work well for videos. In videos, you really need to sort of try to understand the signal, understand motion, and figure out how do you compress the signal, the pixels, together with motions and maybe the changes in these pixels. Right? And so with that, we're sort of at the end of the second part, which is dense regression. Now, if you go back to the image that we had in the beginning, we now can kind of produce all sorts of global labels or descriptions of the image. And we can go in and produce we can paint the image with different sort of outputs or different classification outputs, different regression outputs. We could even just reproduce the image using regression itself. We'll have a little break, and then we'll look at tasks that sort of lie in between classification on a global level and classification on the pixel level. And I guess we can do let's do a 5-minute break, and I'll answer some questions then. Okay, there's a question for monocular depth estimation. Since a single projection can correspond to many depths, this is essentially a one-to-many problem. Isn't it more natural to predict not a single depth, but some sort of depth function? Yes, it is possible to have a distribution over depth. Now, maybe one thing to note, for monocular depth estimation, we actually don't use a lot of geometric cues. The cues that we use for monocular depth estimation, both humans and our current vision systems, are on a local level. This is lighting. On a local level, you can tell from the shading. For example, you can tell from the shading of my hand, you can infer what the shape is. And then the other cue that you use is priors and size. So if something appears small, it's far away. If something appears large, it's close. And sort of priors just being that my nose will most likely stick out of my face. Okay, there's another question. How does saliency work? Yes, so there's two standard definitions of saliency. One is sort of the biological formulation, where you can mount a gaze tracker on a person and then show them a new image and just see where do they first look. What do they spend most time looking at? And then you can get a map of sort of what do humans think is important. The other way to do this is to go on Mechanical Turk and ask them a very specific question, which is, what do you think is the most important thing in this image? And then they will go highlight an object, a region, and so on. And so these are the two different ways to define this. One is biological, and the other one is just through questions on mechanical Turk. But both of them are just trying to mimic the human signal. Regarding data augmentation, is there a specific method for the like of medical images for which subtle changes may change the image a lot? Yeah, I'm not an expert in medical images. I would have to get back to you on this. Is super resolution a dense task? Are neural networks state-of-the-art here as well? Yes, so some people separate out image generation as a separate task and then bundle everything under image generation. Here, I just put it with the dense tasks. It is definitely a dense prediction task. In this case, for super resolution, you would predict multiple outputs for one input. So you would have, if you want to resolve a super resolve by a factor of 2, you'd have four output pixels for each input pixel. And yes, deep networks are definitely state-of-the-art. Yes, regression versus classification. Yeah. Yeah, so there's a nice paper. I think it's called Planet from Google. I can give you the title. It's Planet Photogeolocation with Convolutional Neural Networks. That's a nice pointer that sort of nicely combines regression and classification at a very large scale. Another question is sort of saliency methods used to be sort of one way to look at explainability. And then what is the state of the art for explainability in computer vision for classification and regression, either in the image or pixel level or both? With explainability, do you mean, like if you mean interpretability, there's still GradCam and all of the likes that look at sort of what are the image regions that influence an output decision the most. Another way that people really started to think about explainability is, instead of trying to figure out what the network is doing, just trying to have representations as an output that are very interpretable. That you can go and, instead of trying to see why did the network fail, just try to see kind of what output did it produce, and is this a reasonable sort of intermediate representation? And we'll see a lot of these in the next topic, which is sparse tasks. So these really sort of go away from making things internally interpretable to just mapping it to an output representation that is interpretable. What about using the feature map to find the activated area, so it's gonna give me an attention in some area of the image? Yes, people did try this. Like I'm assuming you're referring to saliency. It turns out actually just regressing to human saliency estimates works quite well. Also, saliency has fallen a little bit out of favor. It is being mostly replaced by object detection and other sparse tasks, which we'll look at in a moment. would an example of an interpretable output be a beta VA? I am not familiar with beta VAs, but I'll look them up after this talk. All right, so let's move on. There's still a little bit to cover, and we'll look at sparse tasks next. And so sparse tasks really fall between the first two categories here, which is they don't produce one single output per image, but they also don't produce an output for every single pixel. And so what you can think of it, they produce an output that somehow groups certain pixels together. It's an output that kind of summarizes a group of pixels. And so in terms of sparse tasks, there's lots of human-centric sparse tasks, which the first one is obviously detecting humans. Here, this would just be kind of finding all the people here. And once you detect them, you can start to analyze humans further. One thing you could do is you could do pose estimation, where you would want to find sort of key points or the skeleton of the human, find all the joints, and their overall pose. You can do this both in just 2D in the image, or you can even try to do this in 3D by inferring sort of their pose as they are placed in the 3D scene. Another popular sort of sparse human-centric task is face recognition, which is either detecting all the faces or even identifying different properties down to the identity of the person itself. Another set of sparse tasks is more object-centric, and by far the biggest here, and this is actually the biggest task in computer vision overall right now, is object detection, where you're trying to kind of localize and categorize all objects in a scene itself. And humans are often also counted as objects. Now, once you found these objects, you could even go and segment them out. And this is called instance segmentation, where you would want to figure out, well, what group of pixels correspond to individual objects. So this might be the group that corresponds to the scooter here. This is the group that corresponds to the person riding the scooter. If you have another person, there would be a different group here. And so there's a very important difference here between instance segmentation, which is trying to group pixels of individual objects or instances together, and semantic segmentation. Semantic segmentation does not distinguish between two different people standing next to one another. Instance segmentation will. So instance segmentation will say this is one group of pixels of person one, this is another group of pixels of person two. Now, you can also detect brands or sort of objects that correspond to brand names. And finally, you could then go, once you detect objects, you can go count it. Now, counting can be both sort of a global task, an image level task, because you just receive a number, but oftentimes it is actually set up as sort of a sparse task where you first go detect the objects and then you go count them. And then there's other sparse tasks. One of them is, for example, lane detection or drivable area detection, where you would kind of want to figure out where here on the road can you drive, which part should you not drive on. In this image, there should be no drivable area. You should push your scooter. But if you really want to drive, you can estimate sort of what is the lanes or the drivable areas you should stay in. You can do text recognition or optical character recognition, where you essentially, instead of detecting objects, you're detecting either individual characters in optical character recognition, or you can detect entire words or sentences. All right. And yeah, finally, I think I have brand recognition twice. Sorry about that. Okay. So again, in here, you have many different tasks, but it turns out that there's actually a lot of structure to the way these tasks are set up so that they become very, very similar. And a lot of these tasks go through through one central component, which is object detection. And so we'll do object detection first, and then we can do a lot of different other tasks. For example, once we know where the object is, we can go segment it. We can figure out what brand it is. We could even go and count all objects. The same as once we detect the person or the face, which the same infrastructure for object detection can be used for person detection. We can then go estimate pose or run recognition. Also, lane detection oftentimes is phrased in a way that is it's a slightly different parameterization of objects. Now, lanes are not necessarily objects, but they can be sort of parameterized in a very similar way to objects. And then again, text recognition or optical character recognition can again be done using just an object detector. And so what we'll do here is we'll first look at how is object detection sort of tackling computer vision. And this gets us sort of more and more away from the traditional machine learning of I just want to map X to Y, and more into sort of the engineering, or if you want to be generous, the AI parts of computer vision. And so the way we're going to sort of phrase the problem is, again, we're going to use a deep network, but unlike image level tasks, we're now going to go and produce outputs that are sort of less structured. So we can have one input image, but the outputs here can have a variable size. It can be a variable size of objects at a variable sort of set of locations. And we're going to have sort of a variable set of ground truth annotations that we need to match, right? And so this really changes the way we think of deep networks. It will change the way we set up the network. It will change the way we produce outputs, and it will even change the way we think about loss functions, right? And so the very first thing we're going to look at is how do we use a deep network to even produce sort of these weird, different sized outputs. And so one way to phrase object detection is to reduce it to classification. But now we're classifying regions in the image itself, okay? So instead of trying to classify the entire image, we now go and look at different regions in the image, and we're asking one simple question. Is this region part of an object, or is this an object or not? All right, so that's the classification problem that we'll phrase. So we'll crop out a region from the image and ask, is this chair or not? All right. Now, one of the sort of immediate things is, well, what happens if we crop out sort of a partial region? Is this here going to be a chair? Or how do we even enumerate all possible regions to do this? Is this an object or not problem, right? So the basic setup is relatively simple. We crop out a single region and just ask, is this an object or not, using a convolutional neural network, right? This is the machine learning part. Now, the harder part here is trying to make this work in practice, okay? Because there is many potential regions. There's actually a quadratic number of rectangles if you look at an image. And most of them are just going to be weird shaped things that contain maybe partial objects. And so how do we go and make this work in practice? So we can easily train a classifier that says this is an object or not, but then running this classifier to detect objects is going to be very hard. And the earliest solution to this was in RCNN, which is just trying to use some low-level vision algorithm to figure out where potential objects might occur. And so these low-level vision algorithms are called object proposal or region proposal algorithms. And what they do is they just look at low-level image statistics to figure out potential regions for objects itself. And what a region proposal algorithm might give you, it might give you sort of a superset of potential objects. And then you would just classify each, from this superset, you would classify each box into, is this an object or is this not an object? And this will give you the ability to go from a fixed size image to a variable size output. And obviously you cheated a little bit because you had to use some low-level vision algorithm to go get you from the fixed size to a variable size output. Okay. Now, the other issue here is, well, what happens if you get overlapping or partial objects? So for example, is this proposal region of the chair more of a chair than this red region here, right? What if you classify both of them as chair? Are you going to now produce two outputs? And again, this is actually a fairly difficult problem. Now, one solution to this is to just say, well, I'm just going to let the classifier decide which region it likes best, and then I'm going to suppress all other regions. And this is known as non-maximum suppression. And this is how it's solved for testing. Now, during training, you also need to come up with a rule that says, hey, is this box a good chair? Is this box not a good chair? And here you'd have to look at overlaps between ground truth and individual sort of predictions or proposals to come up with a rule that says, these I consider as positive chairs, these I'll consider as negative chairs, and then there's some that are in between that I don't know what to do with. Okay, I'll go answer some questions. I think there were quite a few. What do you think about statistical approaches? Could be practical. Can you give me some more context? I don't think I can decipher what you mean from that question. Can I assume a potential region can be an activation region? Yes. So the way region proposals work is they kind of try to enumerate all potential sort of regions. And yes, people have used deep networks, and we'll actually get to this in a moment. People have used deep networks and activations of deep networks to try to zoom in on what potential good regions are. There's a much better way to do this, which we'll get to in 2 slides from now. So this is really just to set up the problem here. Yes, what is my comment on better? We'll get to this in about 10 minutes. Yeah. All right. The other thing with these proposals is that they might not actually cover the entire object. And so oftentimes it is good to go and refine the object or to refine the box and say, hey, I'm start out from this proposal, but really where I think the chair is at a slightly different location. It should probably cover a larger box, okay? And so if you put all of this together, the full algorithm, what RCNN does is it finds region proposals, it crops and resizes these regions, and then it classifies all regions into objects or not, regresses to the exact location, and then finally suppresses duplicate outputs. Okay. And then during training, you assign all objects that overlap with the ground truth, or all regions that overlap with the ground truth with a certain percentage as positives, all that don't overlap with a certain lower percentage as negatives, and then you just train this as a standard classification problem, a standard binary classification problem, or multi-class classification. For each region that overlaps, you also regress to where the actual ground truth object is, right? And so that's how you can go in a very, very strongly engineered way from an image to a set of bounding boxes, all right? So you go from a fixed set image by chopping it up into regions to a variable set of outputs. And this is by no means what people do nowadays. I think in 2015, this was done in 2012, 2013. By 2015, people figured out much better ways to do this, which is the first sort of big issue that was addressed was that RCNN had to look at multiple regions and forward different regions through the network and run about anywhere between 100 to 200 different forward passes through the network, which was horribly slow. And so a much better way to do this is to first feed the image through a CNN and then crop out. So if you feed it through a CNN, you will get some activation map here, which are, you can think of abstract features, and then you crop out these abstract features and just have a very lightweight sort of classifier on top. Now, fast RCNN still used the region proposals. Faster RCNN, which was written 2 weeks after fast RCNN and presented, I think, a week before fast RCNN, also replaced the region proposal with a different classification network. Okay, and what they did is they again used this CNN to produce an activation map. And now for each sort of activation here, they just produced a bunch of proposal boxes around it of various sizes and shapes, which are called anchor boxes. And they classified where they think objects are with respect to these anchor boxes. So they just said, well, maybe at this location, this anchor box might contain an object, or maybe this other one here might. And so you can reduce sort of this proposal step to just classifying a set of fixed anchors into there might be an object here, or there might not be an object here. Okay. And so what faster RCNN now does is it uses a convolutional network to produce an activation map. From that activation map, we produce potential locations of objects by just classifying individual features in this attention map into there might be an object of this shape at this feature location. And then for each one of them, you go crop the original CNN features and classify and regress to the final output box. And so this is now one system that can go from an image to a variable set of outputs. And there's really two mechanisms in here that allow for this variable output. The first mechanism is the region proposal network here, which goes from sort of an exhaustive list of all potential regions around features to sort of a much smaller list of sort of potential object locations. And then the second part, after the pooling, the classifier here will further filter regions into, well, maybe the RPN was wrong here, or this is an object of class of type X. Okay. We still do non-maximum suppression, and all the rest is just sort of a convolutional. All right, I'll answer some questions before I get back to the slides. how is the size of the region proposal determined? Yes, in traditional methods, this is just a heuristic, some low-level statistic that will just say, hey, interesting regions occur around these image features. In modern learning-based approaches, these are just fixed size object locations that are sliding over the window, over the image. Now you do run them at multiple resolutions to get kind of multiple sizes, but initially in RPNs, they're fixed. We'll look at a solution that does not rely on this in a moment. Right. And so sort of these detectors have really been sort of dominant from about 2015 to about 2020. And in about around 2019, there's been a different sort of theme of detectors emerging that did not use the RPNs or these proposals anymore. And sort of the key idea was to reduce object detection to sort of a classification problem of centers of objects. And I think like there's been about 3-4 papers that came up with almost the same idea, and they now almost converged to sort of the same setup, which is instead of trying to find objects as boxes and anchors as boxes, we now just try to find centers of objects. In work we did, we placed the center right in the middle of the object. There's other work that kind of looked at different definitions of what centers are. And now, if you can go detect the center, you can recover the object or the box by simply regressing to the size. So instead of needing to enumerate all possible anchors, all possible box shapes, and you now only need to enumerate all possible centers. And the possible centers are really just possible 2D locations in an image. And the way you can do this efficiently is by just using dense regression to a heat map where each sort of peak in a heat map corresponds to a center. And this is a trick that has been used in key point estimation. So you can reduce sort of this object detection, this sparse task, to a dense regression task where you just say that you only count sort of outputs that are local maxima. So if an output is larger than its 4 neighbors, then it's produced, and otherwise it does not produce an output. And then you just regress the width and height. And so this allows the network to control how many outputs it wants to produce. It can produce a lot of peaks, or it can produce an almost uniform 0 image, and then not produce any box. So this is sort of the second, and by far, I think now it's still sort of the more popular or the more performant sort of way of doing it. And then there's a third way of trying to get to this mapping of one image variable set of outputs that uses transformers. And so that third way is called DETR, or detection transformers. And here, the sort of main idea is, instead of trying to produce a variable set of outputs from just an input, we're now looking at sort of different tokens in a transformer, and we're using cross-attention to transform these sort of input tokens here to individual boxes. It turns out in object detection, you rarely have to go and detect more than 100 objects. So you can just use 100 tokens, or maybe like a few hundred tokens, and transform them into a few hundred boxes. Now for each box, you're also going to regress to sort of a binary classification, which is this box really containing an object, or is this box just there because in some other image it might be helpful, right? And so this is the high-level idea of detection transformers, or DETRs. There have been various different variations of this. The original form, it really just was just a transformer. There's ways to kind of combine them more and more with convolutional networks. And it's still not clear if sort of point-based representations or transformer-based representations are really the way out. What has become clear here is that anchor-based representations are most likely not the way forward. Okay, so that is the sort of how object detection is currently phrased. Now that we have object detection, most other tasks can kind of be built on top of an object detector. And so if you look at the other tasks that we listed as sort of sparse tasks, person detection, this is object detection with just a single class. Object detection is done. Then if you think of sort of face recognition, if you look at face detection, this is again just object detection with a different label. The same for text recognition or OCR. It's object detection, but with a different definition of the object class. Now, there's lots of tasks that are not directly object recognition, but they can be built on top of detected objects. The simplest one here is instance segmentation, which is once you have an object or a box of an object here, you can then go and crop out that region either from the original image here or from the feature map of the CNN. And you can have another second network here to produce an output mask. And so what you're doing is you're using sort of the object detector to do the hard sort of image to variable output mapping. And then everything that follows after that is sort of a simple one-to-one mapping of one object detection to one output. So this works for instance segmentation. You can do this for pose estimation, where you would highlight different key points if you do multi-person pose estimation. You can do it for face recognition, where you would train an embedding of a person or attributes of a face. You could do this for brand recognition, where you could then go classify brands, maybe even sort of embed brands if there's like different embeddings. You could, yeah, I think that's the tasks. Now, a different way to use detections is in counting, where you could just sum them up. Maybe you look at sort of the confidence of each of the detections when you do this. And then there is also lane detection here, which is sort of an outlier because you don't detect objects, but you can use an object detector and modify its output space to then go and detect different sort of drivable areas or lanes. And so really what object detection does, it provides sort of this common framework to do the image to multiple output mapping, and then you can either use that framework in its original form with different labels in a slightly modified form, or you can use it to get objects and then solve other tasks in a one-to-one mapping. All right, so that's sort of how a large portion of the sparse tasks are tackled in computer vision. Let's look at sort of the fun open research that there is in sort of computer vision in these sparse problems. And the first one was already mentioned earlier in the question, which is open set recognition. And really, if you think of sort of what is the most popular thing in computer vision in a specific year, I can guarantee you by the end of this summer, open set recognition will be one of the more popular topics. I know many research groups are currently working on it and have exciting results. And in part it is because there's finally some very nice kind of connections between language embeddings and computer vision that made the open set problem easier. And so what open set recognition really tries to do at its core is trying to build a recognition system that can reason about classes it knows, but also reasons about classes it does not know. And so, for example, you would want to build a detection system that is able to classify not just deer, but maybe if you have a new sort of deer or you have a gazelle that you haven't seen before, you could then go in and say, hey, this variant of deer that you call deer here is actually a gazelle, and you can then go and adapt it. Or the detector could tell you, hey, I think this is an object, I just don't know what it is. And so this sort of going beyond the set of closed form labels that you have in your training data is really kind of what a lot of research is currently looking at, will probably look at in the next few years. There's lots of interesting problems there. For example, how do you reason about things that are unknowns? Like there's different categories of unknowns. There's kind of, how do you reason about the fact that you know it's an object, but you don't know what it is? Or how do you reason about even knowing if this is an object or not, sort of the core definition of objects. And again, the reason why this is starting to get quite popular is twofold. One is because we have good language embeddings, which allow us to reason about objects in sort of in a more abstract way, a way that doesn't involve labels. And the other reason is that object detectors actually have gotten a lot better under the hood. If you look at sort of the transformer style object detectors or point-based detectors, they're starting to generalize extremely well to sort of objects. You might not be able to name all the names of the objects, but you're able to enumerate all the proposals or all the objects in a scene very, very well. And so that's sort of the reason why this open set problem all of a sudden became a lot more popular and a lot more doable. And then the second really big open set problem here is, the second really big open problem is, how do we come up with sparse representations for things that are not objects? How do we come up with sparse representations for things that are maybe unlimited or unbounded? And one example here is lane detection. And in lane detection, this is actually somewhat solved. A lane is not an object. It has sort of it can have an almost infinite extent, but we're able to come up with some simple curves or parametric representations for what these lanes are. But if you would look at this other image here, how do you do this, for example, for ground? Can you come up with a parametric representation that is quite compact that describes the entire ground region? We can do this for deer. We can do this for objects like trees. But how about ground? What about rocks if they're just rock formations instead of individual rocks, right? And so this is sort of the other sort of unsolved problem in this sparse representation. How do you represent stuff? We know how to represent it as a dense segmentation mass, but we don't know how to represent it in a more compact form. All right, with that, we're sort of at the end of the second part. And now if you look back at this image, what we can now do is we can look at sort of global decision problems, global sort of classification problems. We can label individual pixels, and we can label sort of objects or groups of pixels that belong together. What we can still not do right now is we cannot go and label sort of things that extend in time. And that's what we'll look at in the last part. Again, we'll answer some questions and then we'll probably continue in about 5 minutes. Okay. Yeah. So what is the exact mechanism that Detter uses to see what parts of an image the network is looking at when it makes a prediction? Yeah, let's go back to Detter real quick. So the mechanism that connects sort of the proposals here to the image itself is cross-attention. So you'll have each proposal here gets to attend the entire image and attend a specific region in this image. I mean, multiple regions probably, and then aggregate these features. And so you can think of what initially happens in this in Detter is that each of these sort of queries here will specialize in either a specific location, in a specific appearance, and then through multiple layers of cross-attention, it will start to zoom in more and more on that region or that that specific appearance. If it doesn't exist in this image, it might just predict, hey, I don't think I'm an object this time around. If it does exist, it will start to zoom in and localize that part of the image well. All right. I think I'll start now with the final part, and we should still have some questions, or we should still have some time for questions in the end. So the final part is going to be hopefully a little bit shorter. All right. So let's now look at sort of this far we looked at sort of how do we infer things in a specific image. Now we'll look at how do we extend this to videos. And really what we want to do is we want to figure out first what tasks could we do that are of interest in videos. And then we'll go and sort of look at how can we go and solve these tasks. And here we have essentially video level tasks, which are sort of mostly action recognition. If something is moving, if something is changing in the video, kind of sort of the biggest question that we want to ask first, what is actually happening? Like, what is the change? What is the action that is being performed? Now, a slight variation or a slight kind of twist on this task is kind of to do action forecasting. Instead of trying to figure out what happened in the past or what's currently happening, you want to figure out, hey, what might happen in the future? For example, in this image here, you might ask yourself, well, is this person going to crash? Is this person going to stop or get off her bike? Is this person going to sort of turn left, turn right, whatever? Another set of tasks is sort of the dense analysis task, which is dense motion estimation, which is trying to figure out for every single pixel in the image, where did this pixel occur in the previous image? This is often called optical flow estimation. And then there's a very beautiful alternative to this, which kind of combines optical flow estimation with depth estimation. This is called time to contact estimation, where instead of trying to figure out what the motion of individual pixels were, you're now trying to figure out how long will it take until you hit that object. And hit really just means how long will it take until the image plane that you project your image to, or your camera plane, will intersect with that object. It doesn't mean that you actually have to physically hit it. You just have to have the object kind of go from in front of you to behind you. And this is a nice formulation because it turns out it's somewhat invariant to the individual or to the characteristics of the camera itself. You can do time to contact estimation without knowing anything about the calibration of the camera. And so this has been, I think it's best student paper, best paper this year at CVPR that really showed that this is a solvable and also easily solvable problem. Now, other tasks are object-centric, and they're mostly evolved around extending object detection into 3D, which is tracking, and also sort of the forward-facing aspect of tracking, which is sort of trying to predict where things are going in the future. Now, I would love to tell you that for sort of video tasks, this is going to be the same story as we had before, that we're going to have one nice input video, one glorious model that outputs an output, and everything is going to use the same sort of overall structure or setup. It turns out it's not as nice. There is no unifying model currently for video level tasks or for sort of temporal tasks. And the entire field of like analyzing videos in computer vision right now is a little bit disorganized. It doesn't have this common theme that the other topics have. For video level tasks, they pretty much model their networks after sort of image level tasks, but instead of using a single image as an input, they now use a series of images as an input. Instead of using 2D convolutions as basic building blocks, they now either use full-fledged 3D convolutions that can reason about space and time, or use more often 2 + 1D convolutions that kind of decompose the spatial convolutional part and the temporal convolutional part. If you use transformer-based architectures, the story is exactly the same. You essentially factorize the attention of the transformer into attention that goes along time and attention that stays within an image. And so that's how sort of video level reasoning tasks are often tackled. You take an image network and you try to inflate it along the temporal dimension. Now, the issue with sort of video level tasks is that there's actually relatively small data, or there's a few number, like there's no sort of gigantic ImageNet of videos. There is kinetics, which is a fairly large data set, but even compared to sort of moderate size image data sets, kinetics is relatively small. Models, since they now need to reason about space and time, or like image coordinates and time, become very slow, and training becomes longer and longer. And so from many of these video level tasks, really only a few labs in the world can do them with these inflated models. These labs are Google, Facebook, and other big companies. For most other people, kind of trying to compete on this game, video level tasks is going to be an uphill battle. Now, for dense tasks, the story is actually quite different. For dense tasks, there is very nice architectures. They're again very nicely sort of tailored to sort of the structure of the task itself. And two most popular dense tasks are currently optical flow estimation and sort of one version of either time to contact estimation or trying to estimate depth from a pair of images. And the way this is often done is by having a network that first processes like two separate images, a pair of images, and then you feed this into some sort of either Siamese or some sort of network that either uses correlations. In modern architectures, maybe even uses transformers to sort of connect elements from different images. And that network will then produce a dense output, either a motion estimate that says where every pixel moved in terms of optical flow, or a time to contact, which is more like a depth estimate for every single pixel. Here, the challenge is that it's quite hard to obtain ground truth data for all of these tasks. So obtaining ground truth pixel level motion is almost impossible. There's, I think, to the best of my knowledge, there's one data set that provides this. This is Kitty, which uses depth and very good camera calibration to compute sort of motion for static parts of the scene. And then for any dynamic parts, they fit 3D models to cars and then manually by hand move these 3D models through the scene to compute a sort of a rough motion estimate for cars. The better solution here is to actually rely on synthetic data. And remember how I mentioned earlier for dense semantics tasks, synthetic data didn't really work that well because you had a domain gap. Turns out if you look at dense temporal tasks, this is less of an issue. You can do motion estimation, optical flow, and time to contact estimation very well from very weird and simplified synthetic data. And one of the first ones to do this was the flying chairs data set, where they just rendered 3D chairs on top of images and rotated them arbitrarily to generate sort of fake motion of objects. And it turns out if the network only needs to care about where similar moving parts move from one point, from one image to another, it is not bothered by the fact that the data it needs to do this on, it needs to train on is synthetic. And it will generalize quite well from these synthetically generated fake motions to real sort of optical flow estimates in the real world. Okay, question. Are there special reasons why your presentation was? Okay, why don't I talk about math? I personally think math is overrated in computer vision. That's a personal thing. I can go into details of how this is done mathematically, but honestly, for most of the successful sort of computer vision models, math had almost no part in it. Sort of what made it work is a level higher than math, which is sort of overall ideas and concepts. And so in this, for example, in optical flow, what made it work was not the math, which is honestly all there is in terms of math for optical flow is chain rule because you use gradient descent to train it. What made it work was the idea of using sort of synthetic models or synthetic 3D models to obtain ground truth optical flow and then mimic that synthetic data. And the insight that empirically this transfers to the real world. There's no mathematical theory on why it transfers. It's an empirical fact, and there's some intuition behind why this works. But the math itself is honestly not. There's no math. Yeah. There's one topic that needs math, which is compression, and I just didn't want to go into it just because I felt like it was too complex. All right. Let's get back onto topic. Finally, we can look at object level temporal tasks. And here, really the sort of the basic building block is an object detector. And you can extend object detection through time in multiple different ways. One way is to, if you use point-based detectors, you can actually make a detector give you tracking as part of detection, which is you can not just predict outputs as sort of centers of objects, but you can also regress to where did you think the center of the object was in the previous time step. So this is the same as motion estimation or optical flow, but now you just do it for the centers of objects. And this will allow you to then backtrace where the object was before, associated with the previous object, and then get sort of a track through an entire video. This will allow you to follow objects through a video. Now, an alternative to this is to detect objects in two different frames, which is sort of the you do detection first, and then you associate. And this is called tracking by detection, where you use the object detector to give you potential locations of objects, and then you link them up either through an embedding or through some geometric reasoning. Right? So this is how you can extend object level tasks easily into time. And for object level tasks, this is by far the best or the most well-defined sort of aspect of video modeling, because it's easy to annotate data. It's easy to annotate boxes that go through time. It's not very expensive. You can get lots of supervised data, and the task itself is actually close enough to object detection that we have good evaluation metrics and benchmarks to figure out how well we're doing. I agree, does geometry. Right. We'll get back to math later. All right. So before we get back to the topic of math, we'll look at sort of what are sort of the remaining high-level research topics that people look at in sort of video modeling. And one of the big ones is trying to come up with ways that sort of model or process videos in a very nice and compact manner. If you look at the video here on the side, that video actually contains about 2.78 billion pixels. And if you would store it in uncompressed form in raw pixels, it would be about 2.8 gigabytes in size. But on your phone, as you capture it, the video is compressed down to about 18 megs in size. And what that means is that there's about 100 to 200-fold reduction in size. What that means is that the amount of information that is contained inside of that video is about 100 or 200 times smaller than the amount of pixels. Yet, for all of computer vision, we use the raw pixels, we use the full resolution, and run the same model over and over and over again. All right? And so this is extremely inefficient. Now, the main problem is that we don't know how to do this as accurately, but more efficiently. Okay? There's no good way or no good theory on how do you build models that maybe work well on individual images and extend them to videos. There are some attempts on trying to do inference sort of in real time by trying to figure out how long computation takes and then forecasting the outputs, and as soon as it's done, doing the next step. And this way you get sort of interpolated and in irregular outputs, but there's no kind of way to sort of, there's no good way to model the concept of compression or the fact that information is much smaller than pixels inside of our networks. Sort of the second open problem here is that we also sort of don't quite know what tasks or what problems or what definitions of problems that we actually want to solve in videos. And we came up with a list of problems for images, and that list of problems for images covers a wide range of potential applications. For videos, that list is much smaller, and we don't even know if all of them are needed. We don't know where to allocate resources, and we don't even know if there's like a nice definition that would somehow, in the end, unify all of our tasks under a common framework. Okay. And so the most fundamental question is even not known. For example, do we need time for many vision tasks? It turns out for action recognition, you can actually do action recognition quite well by just throwing away time and treating the video as an unordered collection of images. And so even the fundamental question of what is time useful for, we don't have an answer to, right? And so here, there needs to be a lot of standardization inside of video recognition to figure out kind of how do we organize the entire field? How do we come together under a common framework and under a common set of problems? Okay. And with that, we're sort of a bit early, but we arrived at the final discussion. All right. I'll answer the questions that are in the chat, and then maybe you can post some more and we can have some more higher level discussions. Yes, in videos we do have additionally, we have access to audio, and there's actually a very active sort of field of research on how to use both videos and audio together. And you can use, for example, audio to figure out where to look at in videos or what parts, what time, sort of what temporal extent in videos might be interesting just from the audio signal alone. You can use the audio signal to recognize videos more. There's definitely a large area there that I did not highlight in this talk. All right. All right. I'm not sure if I should go into the math or not math. I probably have an extreme stance on math, which might not lead to a good discussion. Yeah, can we use text and images at the same time? Yes, there's a very interesting work or series of work, the latest of which is, I think, the most prominent is CLIP, that tries to sort of use captioning models that look at images and text together and tries to embed them in the same space. This will help kind of captioning models disambiguate different visual concepts that might have the same English word, and it will help vision models generalize sort of between different labels or naming conventions of the same visual concept. And so that is a very interesting direction to go into in terms of kind of trying to connect what language is doing, what natural language processing is doing, and what computer vision is doing. Could you share more about recent advances and the current state of variable input sizes in computer vision? In NLP, there is often no restrictions. Yes. I don't think the input size is fixed in computer vision models. In fact, you can train a computer vision model on one resolution and test it on a much higher resolution. This is often done in object detection. So I don't think there is sort of an interesting, like, or I don't think there's any fundamental limitation to the variable input size. What is your opinion on the recently published MLP mixer networks? Oh, I love the MLP mixers. They're great. Like the fact that you no longer need attention is fun. I think they came epsilon close to completely replacing attention, and then they were just the last little bit that they couldn't beat. Yeah, and then if you think of doing some sliding window transformer on MLP mixer, then you just end up with convolutions again, which I feel like we're sort of back at where we started. But it's definitely very interesting to see sort of people explore sort of these extreme ideas. And in computer vision, we have in the past year, we have had this, that somebody kind of has a provocative extreme idea, and then 100 other people try it and sort of walk it back to something that works better than what we had when we started. This happened with transformers, and it hopefully will happen with mixers as well. Yes, I will make sure that you get the PDF of the slides. It's Keynote, but not PowerPoint, but that should be fine. All right, so. All right, okay. All right, we'll do the math comment if there's really no other comment. I'll get into that. Okay, so why does training on small resolution and low resolution and testing, or even fine-tuning on larger resolution work, and why is it a good idea? The reason for it is that on a smaller input resolution, you'll get a larger batch size, and the network will train faster. And so you can train networks on a smaller resolution that you couldn't train on larger resolutions, or at least not with resources outside of the biggest labs. And so that's why it's often done. If you could train on a high resolution and test on a high resolution, I think most people will do it. It's just too expensive. Right.
I think while we are waiting for the audience typing their probably final questions, I have a very, very general question. We have a general question for most of the speakers. So the general question is, if the student want to learn more about computer vision, do you have any recommended survey paper or textbook or courses they can further to learn more about the modern computer vision?
Yeah. So I really like Rick Zaleski's book. He has a second version of it that covers a lot more deep learning, but it also covers sort of the pre-deep learning. And so that's one I would really recommend, Rick Zaleski's second version of his computer vision book. And I think it should be online as a PDF.
Thank you very much. I think we have more questions in the chat room, but they are kind of mixed with the thank you notes. So you probably need some time to filter those questions from the thank you notes.
Yeah. Okay. Okay, Jan LeCun thinks MLP mixer is a type of CNN. Of course he does. I'm not even sure if that's true. if I want to detect a unique object that has never been trained on famous network, what is the best option here? To train a new network from scratch or tune it? Or use state-of-the-art YOLO? I think the best way to train for new objects is to fine-tune. By now, most object detectors, especially the two-stage ones, are good at finding objects. They will get, I mean, unless the object is sort of really unique, that proposal wouldn't generalize, they will find the object itself. They will just not be able to classify it. And so if that is the case, your best bet is to use a two-stage detector and then fine-tune it. And you might be able to get away by just fine-tuning the classifier of the two-stage detector. MLP mixers using GLO activation instead of ReLU. Yeah, I think most of the transformer-based architectures use GLUs, or they definitely don't use the ReLUs anymore. They also use, I think, I'm not sure if MLP mixer uses AtomW. They use different optimizers, and it just turns out that if you use different activations and different sort of optimizers, it gives you a point or two boost. And I feel like there's just a different local minima for language models that is kind of pulled in here in terms of best practices than there was for vision models, for which nobody really bothered too much, or people did bother to figure out what the best activation this is, but nobody bothered to adopt it. And I think from language and transformer-based architectures, people were a lot more kind of aware of what are the individual small tricks that made it work, and that's why the mixer uses these different activations. What is your opinion on swish activation? Is it better than ReLU in general? Yeah, I mean, it seems to give you the point that you like. If you want a point better sort of numbers on your task, then it seems to do the trick. Is there a fundamental reason for it? I honestly don't know. If I want to detect very small objects, do you have any suggestions? Yes, so for very small objects, my suggestion would be to use an anchor-free method, either point-based or like FCOS or similar, and a high-resolution input. The reason for this is that transformer like Detter style is unlikely going to hit a small object just because it's too hard to transform a query to a very small object. If you use anchor-based one, it's also quite hard to set up the anchors so that they cover all small objects. Okay. Yes, so what is the state of the art for 3D computer vision? I've learned that PointNet is a great model. Yes, so it depends what 3D computer vision you're looking at. There is sort of autonomous 3D computer vision, and there, I think the good models now will use point pillars or voxelnet to sort of try to parse the LiDAR point cloud and then project it down to on a map. And then the head is going to be a standard 2D detector. If you're going to look at sort of 3D understanding of meshes or like smaller point clouds, there is by now a few transformer-based architectures, but I would have to look up the exact citation. I think if you just look for transformer 3D recognition, you should probably find it on Google. I think point transformer might actually be one of the papers. Yes, recently Imagenet was relabeled, or a part of it was relabeled. And sort of, what do I think about these efforts? I think this is great. And the result was actually very encouraging. The result was, if like they labeled I'm assuming you're referring to the Berkeley group that relabeled part of Imagenet, and also I think what other data set to verify how much the community overfits to the data sets that we have, because the community will overfit to test sets over time, because we submit to test sets over and over, and the methods that survive are the ones that are on top of the sort of leaderboard and test set. And I think this is a great effort to sort of control and verify if the community is overfitting. And I think the results there were actually quite encouraging in the sense that we are not, as a community, necessarily overfitting to Imagenet, at least not to a significant degree.
Yeah, we still have a few minutes. So while let the audience type their final question, I have another question. It's also a general one. So as everyone knows that usually the topic, because the result on the ImageNet is very, very good and usually surpass the human level accuracy. So usually the public believe that the problem of image recognition is already solved. But I believe this is not true. I believe the capability of machine is still far from human. So do you have any comment on that? So do you think the image recognition is a solved problem, or what is the difficulty today?
Yeah, I think people outside of the area of computer vision have thought that computer vision is solved for a while. I think there's, in terms of sort of the parts of it that are solved and the parts that are not solved, yes, ImageNet is solved as a data set, or solved. It's at a very good state, but you're not going to drive a car with ImageNet, and so I think the hard problems really only came about in the last few years, which is sort of the long tail, and that turns out to be sort of, if you look at autonomous driving companies, that's what they're struggling with, on the vision end and on also sort of the policy end. But sort of, how do we deal with things that you might only see once in your life? And if you want to deploy computer vision on a car, you need to be able to do that. And because there's always going to be this one weird thing that you haven't seen in this form, and you might not have seen in any augmentation of your training data, that you need to be able to deal with. And I think that answer is both sort of exciting to get at and also like super hard with the current tools that we have. And so if I would want to point at one thing why vision is not solved, that's definitely the one thing. I also would like to point out that there's many tasks that, while there has been great progress, sort of we're nowhere close to being at human level. And in many ways, sort of the way the tasks are set up, it's this beautiful wheel where like we'll have a new data set. In the beginning, everything is hard, then the networks will go up, and then we'll just get a new data set, and we're in the bottom again.
Yes, thank you very much for the answer. Oh, we have more questions in the chat room.
Yeah, so one question is, how can you reach me? I think the best way is email. I'm not very diligent in replying to emails, but if you mention that you were in this class in the summer school, I'll make an effort and reply. Yeah, so one question is, why does medical imaging favor unit architectures? I honestly don't know yet. I think it's in large part, a lot of the mainstream computer vision is a bit hesitant to go into medical imaging because of issues with the data. Like if you had Imagenet for medical imaging, I'm sure we would have all sorts of fun architectures on medical data. But since most of the data sets are not as accessible as Imagenet, it's not just, hey, I'm just going to use a data loader in PyTorch and I'm going to get that data set. It might just take much longer for our architectures to be validated in these settings. And one thing about UNet is actually comes out of the medical literature. It was first published in a medical journal, and so that's why it's popular there. What are your general ideas on how to do large-scale data-efficient computer vision training? What are general patterns there? Honestly, I have to say I don't know. We're currently just wasting GPU time and hope that it doesn't take too long. I think that's the current mode. In your opinion, with the recent advance in computer vision, it transforms in computer vision, is the future of conv bleak? That depends on who you ask, I think. Definitely have colleagues who are like, yeah, transformers is all we need. I'm more sort of the opinion that sort of the middle ground right now seems to win, which is swing transformers, which is some concepts from convolutions, which is sort of sliding windows, but then the basic building blocks can be transformers. It can be whatever else people come up with. But I don't think that actually is the right sort of battle to fight. I think you should just be opportunistic and use the thing that works best. And if it's not ConvNet, I'm not going to lose any sleep over it, because it's still going to be a network that takes an image and produces some activation maps. And I'm still going to be able to do my computer vision using sort of almost the same tools as if I would have used ConvNet. And so I don't think, even if we lose convolutions, we don't need to be sad about it. Whatever replaces it is going to be more awesome. Are there any known alternatives to the UNet building block patterns? You mean sort of downsampling and upsampling? There have been recently some interesting sort of variations on how do we do this sort of downsampling and upsampling of the spatial resolution with transformers. And I imagine with transformer-based architectures, the routing is going to get a lot more interesting. In terms of the general concept of trading spatial resolution for channel dimensions, I'm not sure if we need to change that. Yeah.
I think we still have only 1 or 2 minutes. So if the audience want to type your question, this is the last chance. So I would like to ask a question, and after my question, we will not accept new question from the audience. So if the audience have any question, you grab this final chance to type your question. So my question is, we just talk about the one-shot learning. We just talk about machine have to detect something it has never seen before, just seen once. So do you think meta learning is one way to solve this problem, or are there any good research direction try to tackle this problem?
Yes, I think meta learning is definitely one option. Is it the only one? Probably not. And I think it depends on how you set up the problem. And so there's sort of meta learning sort of tries to get at the problem more through sort of generalization outside of your, like you're trying to find something that's generalizable outside of your sort of current domain. If you look at sort of other approaches like language or using multiple data sets, there you just say, I don't care about generalization. I'm just going to span the entire space of possibilities, of possible domains that I care, and I rely on the interpolation of the network to do sort of its job. In the end, I think we need both. If I have to bet on one, I would bet on multiple data sets right now, but I'm not going to bet.
Thank you very much. Do we have more questions here? We have a less few questions. So to the audience, we do not accept new questions because we are running out of time. So we do not accept the new question. We have the last few questions in the chat room to Professor Philipp. Thank you.
Okay. Does pixel shuffle based up and down sampling a good idea? Okay, I don't know how to answer this question, and I'm sorry, Roman. In general, if both segmentation and object detection labels are available, which task might be harder, detection or segmentation? That's actually a very good question. And it depends on what you want to use it for. And so I personally like detection more because it gets at the individual instances, which gives you slightly more information. But it turns out in certain circumstances, segmentation might be a better intermediary to an end task. If you think of navigation, there has been work that showed that you can do sort of transfer from simulation to the real world if you go through semantics in the middle and through semantic segmentation. And so in that regard, it is a good task to sort of to a final goal. It also captures some of the invariances that you would need at a lower level. Object detection is at a bit at a more abstract and higher level. That's why I like it, but it's unclear if it's really more useful.
I think you have answered all the questions in the chat room now. So thank you very much. Thank you very much that you give us a very well-organized, amazing tutorial over the computer vision. So to the audience, this is the end of this lecture. Thanks, Professor Philipp, again. Thank you very much. Thank you.
Yeah, thank you. Thank you for having me.
Thank you. Bye-bye. Oh, thank you very much. You talked 3 hours non-stop. So I believe you are already exhausted.